In this lesson, we're asking what is necessary to prove a statement true, and so far you've seen how to justify the steps of an algebraic solution. Next, we're going to learn about some different proof formats, and we're also going to learn about how to prove a statement with justifications like propositions, definitions, and theorems. There's some very important properties of equality and congruence that we need to learn because they'll be very useful to us when we do proofs. The first one we should talk about is called the reflexive property. And even if you've never heard this name, you might be familiar with it when it comes to equality for real numbers, for example. I can say that any real number x is equal to itself. For example, the number 7 is most certainly equal to itself, and I don't think anybody would argue with me about that. Well, we can say the same type of thing for congruency. I can say that any geometric figure is congruent to itself. So for example, angle ABC here is congruent to itself. And along the same lines as the real number example, I also know that the measure of angle ABC is equal to the measure of ABC. These are properties of equality and congruence. Next, we can talk about the symmetric property. The symmetric property states that either term on both sides of an equality or congruence statement can just be interchanged. So for example, if I know that xy is congruent to mn, then I can rewrite that as mn is congruent to xy, and the statement is actually equivalent. We already know that this is true in algebra, for example. If I had that 12x equals 5, we might, in one step of our equation, we might need to write that 5 is equal to 12x, and we would know that it's an equivalent statement. And in geometry, for a more geometric example, if I knew that the length of xy equals the length of mn, well then surely I know that the length of mn is equal to the length of xy. There are two more properties I'd like to tell you about. The first one up here is the transitive property. The transitive property is very useful for us when we're doing proofs. And this is what it says. It says that if we know that xy is congruent to mn, and I can write that over here with a sideways congruency mark, and if I also know then that mn is congruent to AB, let's write another sideways congruency mark because I want you to see that what I can do is follow those congruencies down and get a congruency between xy and AB. The same type of thing is true for real numbers. If I had three real numbers, x, y, and z, and I knew that x is equal to y and also that y is equal to z, well, then what I can say is that, well, that means that x is equal to z. The last property we can talk about here is the substitution property. And it's very important for us to emphasize that in general, this is a property only of equality. And this is what it says. It states that if x is equal to 3 and if x plus y is equal to 12, well, what I can do is substitute in 3 for x and say that, well, that means that 3 plus y is equal to 12. And we can maybe see why this is not really true for congruency in general, because we might need to consider the coordinates of the figures that we are talking about. And if I had two congruent figures, such as line segment xy and mn with different coordinates, clearly I cannot substitute them into any type of congruency or statement involving the coordinates of those objects.
I'd like to tell you about deductive and inductive reasoning. Deductive reasoning is the process of utilizing facts, properties, definitions, and theorems to form a logical argument. And it works in the top-down direction. We start with our facts and our givens, and we use deductive reasoning to make conclusions. For example, I've got a friend, Julia, and she hates getting wet. So whenever it rains outside, she has a rule that she must have her umbrella. So when I look outside and I see it's raining, I know that Julia probably has her umbrella. And when I make that conclusion, I'm using deductive reasoning. Let's take a closer look. We're used to this type of reasoning in mathematics whenever we solve an equation using properties and we justify our steps along the way. Or when we prove that two segments are congruent by using information that's been given to us in a diagram. We can contrast all of that with inductive reasoning. This is the logical process of making generalizations based on observations and patterns. It's a type of reasoning we use a lot in daily life. For example, most of the basketball players I've ever met are over 6 feet tall. So, if I meet a basketball player or I hear about a basketball player, I'm probably going to conclude that he's over 6 feet tall. When I do that, I'm using inductive reasoning. This process clearly does not lead to conclusions that are always correct. And for that reason, we don't really use it too much in mathematics. But we sometimes use it to examine a pattern, to write a rule, or to make conjectures based on examples. So what I really meant is that we don't use it to write proofs in mathematics. And in this lesson, especially, we're only going to be using deductive reasoning for our proofs.
Mathematical proofs involve given information in words or a diagram. When we take information from a diagram, for example, if I'm given a diagram of an angle, we have to be really careful to only use the information that's given to us. This looks like a right angle, but it really could be 89 or 91 degrees. Unless we're told that it's a right angle, either with an angle marking or with an angle measure, we can't make an assumption about it. Proofs also involve a statement to be proven, and we prove that statement by making an argument using deductive reasoning, and we justify our steps in a logical order using things like definitions, propositions, theorems, or even other steps of our proof. After we've done all of that, we'll reach a conclusion, and we can use that conclusion in other proofs. Let's go ahead and see what a mathematical proof looks like. I'd like to show you how to use our two-column proof tool. Here, we're going to prove a statement, and let me demonstrate how this works first. A two-column proof is a type of proof used very widely in geometry. It has two columns, and in the first column, we put statements that we are given or that we're deducing, and then in the other column, we put the reasons that we're able to make those deductions. Well, in this tool, you see that I have an area with different tabs. In this case, I have two of them. Sometimes you could have more, depending on what you're asked to prove. And each tab contains a number of tiles that I can tap on and then drag. So what I'm going to do here is start arranging my given information. This problem asks me to prove that given if AB is congruent to CD, just like I dragged down there, but also if EF is congruent to CD, what we're asked to prove is that the length of AB is equal to the length of EF. Let's go ahead and prove that. Here I put in my first statement, and let's see what happens if I try to justify this with the transitive property. That's incorrect. The right answer here is given, because that's given information. And after I click on that check button, it says the statement is correct, but the reason is wrong. So if I click on clear, notice that the reason was cleared away from me. Let's put in the correct reason. This information is given. I notice that that check button appears, so I click or tap it, and the computer tells me that I'm correct. Assemble the next statement. Let's assemble the next statement, which in this case will be the other given. So I write that EF is congruent to CD, and the reason is that, well, it's given to us. At this point, I would like to use the transitive property because I have two line segments both equal to, congruent to a common line segment. However, I can't use it directly. What I need to do is first rearrange step 2 into a more suitable format. I'll say that CD is congruent to EF. And the reason here is the symmetric property. After I've done that, I'll check, and I see that I've made a mistake, and the mistake is that, notice how on EF, I dragged down the length. I really meant to drag down that line segment CD is congruent to line segment EF. It's very important that that we all pay attention to the notation on these tiles. So I check it, now I see that it's correct. I'm happy the computer's here. And let's assemble this next statement now with the transitive property. I want to say that AB is congruent to EF. And the reason here is the transitive property, and it's correct. At this point, what we can do is use the definition of congruent line segments to say that, hey, those two line segments are congruent, so that means that they must have equal lengths. So I'll drag those tiles down and check it, and I see that the proof is correct. Now, why don't you go ahead and practice using this tool on your own? There are many types of proofs in mathematics aside from two-column proofs. I like to tell you about paragraph proofs, and we'll learn about them by proving this statement right here. We're told that line segment AB is congruent to CD, and then we're also told that another line segment EF is congruent to CD. What we're asked to conclude is that the length of AB equals the length of EF. I've already got our paragraph proof started. I wrote that we are given that AB is congruent to CD, and also that EF is congruent to CD. What we're going to do next is we're going to use the definition of congruence to turn those congruency statements into statements about lengths. So by the definition of congruence, we can say that, and actually let's write that this is by the definition of congruent segments. What we can say is that the length of AB equals the length of CD, and also that the length of EF equals the length of CD. Now, when I look at those two equalities, I see that I can substitute EF from this expression or equation into this equation. I wouldn't have been able to do that with the congruency statements because substitution property is only for equality. So let's go ahead and we'll say that now using the substitution property, and I'll abbreviate it again, what we'll conclude is that the length of AB equals the length of EF. And that's precisely what we needed to prove. So this concludes our paragraph proof, and next you should practice a paragraph proof on your own. I'd like to tell you about a cool kind of proof that we use in geometry called a flowchart proof. This type of proof arranges the steps of our proof in a visual way that allows us to see how the proof works logically. We're going to use it to prove this fact right here. We're given that line segments AB and CD are congruent, and we're also told that line segments EF and CD are congruent. What we need to conclude from that is that the length of AB equals the length of EF. So what we're doing here is we've already arranged the information into these boxes, and we're going to justify each step. This first box right here, well, that's the given information, so we can write given underneath that box. And if we look closely at the given information, you'll notice that we have two line segments, AB and EF, and both of them are congruent to the same line segment, CD. If you're thinking ahead a little, then you might realize that, hey, we can use the transitive property here. Now, if you'd like that to be a little simpler to see, then what we can say is that okay, CD is congruent to EF. That is, we can switch the order of those line segments in the congruency statement. And we know that we can do that by using the symmetric property. After that, it should be clear to us that the transitive property allows us to conclude that line segment AB is congruent to line segment EF. After that, we can use the definition of line segment congruence to say, okay, those line segments are congruent and therefore they have the same length. So we can write definition of line segment congruence. And I'm abbreviating it here like that. Now, there was a number of other ways that we could have proven this, for example, by using the substitution property. And I already said that we could have skipped the symmetric property, turning this into a three-step proof. The point is to make sure that your flowchart proof is accurate and that it shows the main ideas. You've been doing an excellent job so far answering our question, what is necessary to prove a statement true? We've seen that we'll be using three types of proof formats to prove statements, and we'll do that by using properties like the transitive property, symmetric property, and the substitution property. Next, what we're going to do is we're going to practice more proofs, and we're going to learn other properties that we can use in them.
Hey, so say you've got to prove a geometric statement. Well, you probably get a diagram, right? Something to show the given statements in action.
But with a diagram, it's easy to make assumptions.
And that means,
You may come to some inaccurate conclusions.
yeah, just because things appear a certain way in a diagram doesn't mean they actually are that way.
So what can we assume? Well, with this diagram, we can assume the points are on the lines they look like they're on. Point A is on line AC, point B is on line BD, and so on.
We can also make assumptions about adjacent angles, angles 1 and 4, and vertical angles, 4 and 2. How they look on the diagram is what they are.
Linear pairs, collinear points, and opposite rays are also assumptions we can make based off a diagram.
So yeah, diagrams tell us a lot, but they don't tell us everything.
Like segment lengths. We can't estimate how long a segment is just by looking at the diagram, even if we pull out our rulers. Diagrams may not be drawn to scale, so unless you're given a measurement, you simply can't know the length.
Same with angle measures. Lines may look like they're forming 90-degree angles, but if the diagram doesn't indicate the measurement, we can't assume they are as they appear.
And when it comes to parallel or perpendicular lines, no matter how they look in the diagram, we can't know for sure unless they're identified one way or another.
So to recap, you can make some assumptions based on a diagram. Things like adjacent and vertical angles, linear pairs, collinear points, and opposite rays.
But even with all that, a diagram doesn't allow us to make assumptions about segment measure, angle measure, parallel lines, or perpendicular lines.
That's all. Thanks for watching.
Let's see how we can do a two-column proof by taking some information from a diagram. Here we are given that C is the midpoint of line segment AB. And then we're asked to prove that AC is equal to 5 centimeters. So we're asked to prove that the length of that line segment equals 5. And if you look at the diagram, you can see that the entire length of AB is equal to 10 centimeters. That information is just given to us. And I've assembled this information over here in steps 1 and 2. We're going to use this information. First, we'll use the fact that C is the midpoint of AB. That means that the length of AC is equal to the length of CB. That's by the definition of a midpoint. Next, what I can say is that, okay, if I sum up the length of AC and the length of CB, that's equal to the length of the entire line segment. You'll remember that that's the segment addition postulate. After that, I'm going to use the information from steps 2 and 4 to conclude that, okay, this means that AC plus CB equals 10. Notice that I'm just substituting in 10 for AB. And I also want you to notice that I don't have to use information that's on the immediate step prior. I can combine step information in any way that I like. The reason this is true is the substitution property. Next, what I can do is use the substitution property again. I'm going to substitute in AC for CB. in step 5, and I'm taking the fact that I can do that from step 3 and also the substitution property. Now what I can do is combine like terms. I have an equation here that is to say that I can add AC together twice, or add it together and get 2 times AC equals 10. Now all that I have to do is divide both sides of that equation by 2. When I do that, I get that AC is equal to 5. Our justification for that step is the division property. This is precisely what we were asked to prove, and so now our proof is complete.